Today we're going to look at how you measure things with digital calipers. And digital calipers are really nice because they have both inches and millimeters on there, but there's more than one way to actually measure things with them. The really good thing about them is that they're rated at 6 inches or a little over 150 millimeters, so they're very nice because there's a lot of parts that you can measure. Anyway, what we're going to look at, first things first, on and off button, very important. Turn it off, turn it on. Okay, that's very easy. One of the things that you have to consider when you're looking at these, you can figure out whether you want inches, will have extra zeros, or millimeters, but when you turn these calipers on, they don't seem to know where you are. So if you turn it off and you turn it back on again, it seems to think that it's like a reset, and now it's 0. So when you go all the way back, now it shows that it's negative 28.9 millimeters, which is kind of strange. All you have to do is hit the 0 key again, or you can turn it on or off again. The 0 key is very important sometimes when you're measuring things, and you want to know the difference between two things. So anyway, let's take a look at it. If you look, there's 3 main ways that you can actually measure things with digital calipers. Okay, the first one, of course, is the one that looks most obvious. You kind of like use it like you would use a wrench. Okay, you got to make sure your little lead screw here is a little bit off, and you can use this thumb screw right here that kind of allows it to go back or forth. It's kind of nice when you're really just barely wanting to creep it up. If you can, you can push it back and forth, but it's very hard to get it exactly where you want. Okay, and so it's very important to be able to move it back and forth. So if you're going to actually measure something, I usually hold it, and like here's just a 608 ZZ skate bearing like you'd see in regular skates. And so if you want to, you just kind of hold it with the thumb screw only, and I've got the rest of my hand just holding the rest of it, and these are supposed to be 22 millimeters, and that's pretty close. Okay, so on the inside, outside things, those are pretty easy. Let's take our cheap disposable debit card. Let's see about this thing. Okay, and 53.94. That doesn't really make a whole lot of sense in metric, so let's see what it is. Oh, in inches. It's 2 1/8 inch. Okay, so 2.125 is what it comes out at. Okay, so you can definitely tell that credit cards were made in the United States. Okay, and then you go over and you can measure the outside. That's pretty easy. It looks kind of like a wrench that way. So here we go. It's about 3 3/8 inch. 3.375 or 85.54 millimeters. That's pretty good. You can also measure the thickness of things. It's very nice to be able to measure, the thickness of it. But where it really comes in handy for rep people is that you need to be able to measure your calibration parts. That's first and foremost, is to be able to use it for measuring filament. Okay, so this should be 3 millimeter filament, and we've discussed this before. It is never 3 millimeters. It is 2.83 millimeters. And you turn it around, 2.82. You should actually hold it kind of like this, so that you're a little bit perpendicular to it. 2.87, 2.88. It varies. And then what I do is I not only measure at one place, I measure it about 4 or 5 places. So I'll go, instead of going, only about 30 centimeters away from that, what I'll do is I will go maybe about 5 meters, and then I'll take like 2 or 3 instances over the course of a spool. Wow, look at that. 2.78. That changed dramatically. Okay. But if you go this way, 2.81. So if you went back originally and you were like, hey, this is what it's going to be, and you measured it, and you'd be like 2.85, by the time it gets down to the 2.78 range here, then you've got less material that's actually going to go into your print, and so that can be a problem. So anyway, so that's 3 millimeter. Well, most I think now all maker-bought machines, and then a lot of rep machines use 1.75 millimeter. And this stuff is smaller. It tangles easier, but the extruders that they put with them just cannot handle 3mm stock, and so 3mm is considerably cheaper. And what do you know? It doesn't come in at 1.75mm. So we're going to just make sure that this zeroes at 0, 0. So it's still got it on the millimeters. You can see millimeters there. If you switch to inches, it has IN down in the bottom. So millimeters is up in the other upper right hand corner. And so what we're going to do is we're going to measure it just to make sure. Yeah, sure enough, not 1.75. It's depending on how tight you make it, 1.72 to 1.73, and same deal. You go around and you kind of like turn it around, so you can see it varies like 0.01 millimeters as you twist it. And then I'll go, same deal. This time I'll probably go, 3 or 4 places in the spool that are, a dozen meters away from each other, and anyway, it's about 1.72 there. So what you'll do is the 4 or 5 places that you kind of check, you want to make sure that you don't just put the very first number. You want to average them out. So you add all of those together and you divide by the number of instances that you've measured, and that will give you a good average. And now that will get a good, pretty good baseline for where you're going to actually put into your slicing program, and that allows the slicer to accurately figure out the amount of cross-sectional area that this has, but it allows it to figure out how much volume of plastic is going to go into your print. So anyway, so there's first and foremost, that is one thing that you have to know. I mean, a lot of people, if they don't have calipers, they just guess, and guessing is a really great way to make sure you never get great prints. So anyway, we're taking the guesswork out of it, and we're going to give you a pair of calipers to be able to measure it. So that's one thing. Actually, one thing that's kind of nice is to look. It comes with a carrying case. Carrying cases are very, very good because these are pretty accurate, kind of precision ground on all the faces and stuff. And so you don't want to get it dinged up. You don't want to get it broken. So you put it in your carrying case. These also come with an extra battery, so when it comes time that the battery dies, which I don't know, this one's never died yet, and I've had it for a year and a half or so. Anyway, when it comes time to change out the battery, this little battery cover, you just slide it off. It takes a little bit more than the thumb pressure, but you slide it off and you pull the old battery out and put this new battery in, and you're good to go. You don't even need to take a trip to the store. So anyway, if I leave this on, if you see there, and I close the cover, and I come back, 10-15 minutes, this actually has an automatic off, so it's kind of a nice little battery saving program that's on there. Anyway, so the nice little carrying case, use it. I mean, that's what it's there for. Maybe it'll actually extend the life of it. So anyway, so there's one way, is measuring the outside. You see it has pointier things on the middle, and that's kind of nice to be able to get into grooves and such. And so for long things, the outside, things that are big diameter that you can't quite get in, for instance, this spool, you look in there, that's pretty big. And so you kind of want to make sure that it could get pretty close to the inside diameter. And so you measure it, if you can hold it, right? And I'm going to pull it out because you can't really see it that way. But you see, it's probably a 90mm spool internal diameter. 3.5 inches is probably more correct, and the reason is because this spool was made by an American manufacturer. I can guarantee you that it's 3.5 inches. It's kind of nice if you want to be able to measure other things. Okay, so if you're measuring the outside, you use this part, okay? And you can measure the outside parts of things really nice. That's called, that circle on the outside is called an outer diameter. The circle, how far across the circle it is called a diameter, okay? So we're measuring the outer diameter, which is the outside, and bearings are kind of nice, and you'll see a lot of things in nature, or in other engineering things. How about tape? You can see the outer diameter here is just the outside. Well, that's only one diameter. You see, if you look, there's like several diameters. You know, the outer diameter of this is also, for the spool, the core, is the inner diameter of the tape. And the inner diameter of here is very important too, because you know you need to be able to know what it is for putting it on a tape gun, or figuring out how much tape you still have left on the spool, if you can figure that out. So we're measuring the outer diameter, and we'll go back to millimeters. 22 millimeters, dead on. So that's perfect, because it's supposed to be a 22 millimeter bearing. But we can measure the thickness of this, and it should be 7.0. 7.01 is pretty close. Yeah, 7.0, depending on when you get it. Sometimes you can slide it back and forth and you can see, and you kind of open and close it a couple times and you can see, for some reason that might be a little out of tolerance, but 7.02, it's still pretty close. But the inner diameter is just as important, because we want to know what that inner diameter is if you want to put it on something like a bolt. Okay, so we want to make sure that this bearing is going to be able to fit on this bolt. Maybe we got the wrong bolt, you know, but we kind of need to know exactly what it is. So let's measure the inner diameter, so the inner circle of this, and we put this together and we kind of wiggle a little bit, and it is 8 millimeters if you look there. So 8.01 millimeters. We'll do it again a little bit, and you just barely kind of want it on there. 8.02, that's pretty good, because this is supposed to be an 8.0 millimeter inner diameter, 22 outer diameter, and 7 millimeters for the width. So this is, you know, pretty close. It's probably totally within spec. And so let's figure out bolts. These two bolts look pretty much the exact same. I mean, they're about the same length, same width, and all that. The difference, though, I can tell you ahead of time, is that one is metric and one is standard. So which is which? Well, I mean, if you happen to be around them, you can tell that the one that says 8.8, that one's metric. So you'll have, if this will actually zoom up on there, that this is metric, this one isn't. But if you didn't know that, you could find out with your calipers. Okay, so let's measure the shank size of this, and it says it's a 7.68 millimeters. Well, an 8 millimeter diameter bolt will not be exactly 8 millimeters, because if it were, this is 7.82, and so you know that millimeter, 8 millimeter, is bigger than 5/16. So you can tell just by that that this one would be, of course, your metric. Well, if you didn't know that, you could also tell by tooth per inches. So the number of turns per inch that it has, some people call it teeth per inch. You can see these don't mesh well. Okay, let me see if they'll actually zoom in. These don't mesh well, and the reason is because they have totally different threads per inch or threads per millimeter, you know, from one to another. Well, one of the great things that you can do is you can use the pointy pieces either on the insides or the outsides, and you can try and get it right in the middle of two threads. And the more threads you can put in between, usually I pick like a standard number like 10, you know, because it's easy to divide, you know. If I happen to have 10 of them in between, then I'll go through and I'll figure out exactly how many it is, and this one is about 12.89 for 10 of them, I think is what it is. And so that makes sense. For an 8 millimeter, it should be 1.25 millimeter per turn going around it for each one of these. So divided by 10, that's pretty close. So I'm sure if I actually sat there and took the time to line this totally up, I would find it that it is right on 12.5. But it gives you a pretty good estimate. So there you go. There's, you know, you can see what size the head diameter is, because the truth is, if you can't measure something, you can't actually build parts to go with it. Okay, so you need to be able to measure things like that. For RepRap, once again, one of the things, first things that you'll actually end up printing is a calibration cube. So, calibration cube, this is a 40 millimeter, 40 millimeter, 40 millimeter calibration cube. I usually start off with like a 15 millimeter cube or a 10 millimeter cube, just because it takes a whole lot less time, and it's good to give you a general guidelines as to how close you are to what you need it to be. Well, if you were to try and measure this with regular tape measure, good luck. You'd be lucky to be within a millimeter of the thing, let alone be accurate enough to judge what your layer heights and stuff are. So anyway, this one was probably the very first cube that I ever printed. You can see it's still got a little bit of blue tape on there, and I don't print too much on blue tape anymore. So what we're going to do is we're going to make sure these say millimeter, and we're going to actually measure it. So let's start off with the X or Y. One of the things I do when I'm actually printing it is to, while it's still on the bed, I'll put like Y on this side if it's Y going forward and backward, and X on this if it's the side to side, for it. And then Z, of course, is, easy to tell because you can see the very small lines in between. Now, white's probably not the best color for this, but anyway, let's measure it. What we don't want to do is this has slightly little ridges here. We don't want to actually measure ridge to ridge. We want to measure the middle part here. So what we're going to do is we're going to kind of like turn it a little bit so we can get at it, and we're going to measure our 40 millimeter cube. Comes at 39.59. That's actually pretty good. I mean, if all you wanted to do is just have fun with it and you didn't really care about the dimensional accuracy, that's probably close enough. But if you really care about how big things are and that you're spot on for whatever you're trying to make, you can then take this, 39.59 and measure it in 2 or 3 places just to see. There's 39.61, and you wiggle a little bit and you'll see 39.62. Take the average over 3 or 4 different places and even turn it upside down, but make sure you miss the edge or the ridge on the bottom, and that's where it's got a little bit of relief in there, and it's pretty easy to tell. And that's a little bit bigger, but 39.73. So you can take the averages of those and you can find out, okay, so there, let's assume that's the Y. Well, then we need to know how big it is this way. So we're going to go ahead, and most belts and pulleys and stuff are the exact same, but if you get a little bit of slack or whatever in between, well, this says that it is a little bit off, and that could be because this was printed on an original prusa, and so it's got what's, there's a little bit of Z wobble in it. And so 39.6465, that's pretty close too. Okay, so we turn it the other way and we go 39.64. Okay, so that's actually pretty close. So chances are that was the exact same pulley dimensions on either way. So now we're going to measure the Z, and the Z is important. If you already know how many threads per inch, or turns per inch or turns per millimeter you have, then this should be pretty close. If you've already put that in your firmware, then that should be spot on. So sure enough, it comes out at 39.99. So that's about as accurate as you can get for a 40 millimeter cube. So the Z height is spot on. The X and Y could tweak a little bit, but truthfully, that's actually not a bad calibration cube for a first one if you had to make it. So anyway, before I go full out with a full 40 millimeter, what I'll do is I'll actually kind of approximate a little bit. So we'll do 40 millimeter in one dimension, 40 millimeter in another dimension, and this should be 10 millimeters. So it's 1/10 or 1/4 of the 40 millimeter, but it prints 1/4 the time. So, and you can see this one was off. Okay, and probably it was because the very first layer was off. But it could be that it just had the wrong teeth per inch. So anyway, if you go through and you see, you want to make sure that whatever you're calibrating, that the X, Y, and Z, you calibrate each one of those 3 dimensions. So anyway, so there's one of the other things that you need calipers to be able to tell, because if you were to just measure this and see, you'd be, close enough. And then you measure it this way and say, yeah, it looks about close. And you measure it the third way, you would never be able to tell the difference between 10 millimeters and 10.39 millimeters. It's just, too subjective. So we want to take the subjectivity out of all of it and give us accurate, truly accurate and precise measurement of it. And the way to do it is digital calipers. Okay. So that's enough of measuring outside. Inside stuff, there's a lot of different things that you can measure on the inside, okay? For instance, well, we already went through that we wanted to do like bearings. How about the roll of tape? Because maybe you want to put a tape holder or build a better tape holder or something for your tape gun. You can measure the inside diameter. Now, one thing you don't want to do is like really crank this screw, because, you know, measure something subjective like cardboard, you can actually deform it pretty good just by squeezing it. So you just, you know, you want to always use, you know, kind of a firm pressure, but not a whole lot of excess pressure. This says 76.8 millimeters, and so that would be a 3-inch core. So once again, United States inches rule over here. So. And same way, you can measure, you know, electrical tape. If you want to make a little electrical tape gun or dispenser, you could do that. The blades of this, you know, it's very hard to measure the outside of the blades. I mean, you could measure the outside of this and the outside of that and the overall outside dimension and the outside dimensions of these two, and then approximate and say, well, hey, each one of these three look like they're equally spaced, and then guess. Guesswork's not really good engineering. It's definitely not good reverse engineering. What you want to do is use your inside measuring, and you can tell 4.56, 4.52, 4.6. Yeah, chances are they were the exact same, just a little bit of variation, you know, in the way it was printed. It was printed on blue tape, so there's going to be a little bit of play like that. But what I did was I actually made this whole thing from scratch. It didn't exist before I made it. I happen to have a child that said that the windmill I was putting in this golf and miniature thing I was building, a miniature golf course, that it needed a windmill. I knew that for sure, but they said that the windmill actually needed to have a motor in it and would turn. And so, well, what I did was I took the cheapest servo I could buy from Hobby King, and I decided I would actually make it snap fit in here. And I actually made a really aggressive snap fit. But I also wanted to be able to, you know, make sure that the battery would fit in there. So what I did was I measured the outside diameter of the battery to make sure either a AAA or a AA battery would fit in it. And then I measured this so that I could tell from the hole that it actually fits in to everything that it took to get this to snap fit in. I went through and I measured up the servos to figure out all that. So 12 millimeters, you know, and then I measured the face from the back part of this. I measured the diameters, you know, there's a double diameter core that had to go in. And when I was done with that, I ended up with a part that this was like one of the first prototype parts, and where you can see that it actually has little stanchions there that it can, the standoffs actually block it in place. You have a compound hole here where you have a main diameter and then a micro diameter, and then you had the overall distance between these that was different. When I measured the part, I measured the outside dimensions, but when I measured the servo, I measured the outside dimensions. But when I measured it to make sure it would fit in here, then you reverse and you start measuring all the inside stuff. And so when everything measures out so that it had all of the tolerances that I put into it, see 12.38, I needed to give it a little bit of space. 0.38 millimeters is not a lot, okay? And then you can see there's a little standoff on the back, and then there's a pocket inside there so that it was big enough that the batteries could go in there. So this is one application. I also needed to have a hole underneath so that it would allow a golf ball to go through there. So when all said and done, then we ended up with a windmill, okay? Well, then again, I need to have, you know, the blade fit on there, so I measured all the pieces for that and had it fit. And then I measured up a little doghouse thing. And see, it's got a little notch out of there. I needed to measure all those pieces, and when all's said and done, it just kind of sits on there. So there you go. Kind of looks like Snoopy's windmill if he had a windmill. So anyway, then the very last thing that you need to know about this, and very few people even know that it's there for it, is to be able to measure with this piece here that comes out. And this is actually to measure things like blind holes. And what blind holes are good for is to measure from, say, the face of here to how far back it is. Because, I mean, you can measure this, and you can measure the distance between the two, but sometimes you need to know the difference between that face and this face, so you just put that in there, and you end up 43.6 millimeters. So, other way that you would need a blind hole, this is a Greg/Wade's extruder, okay? Well, this is where it still has the filling in there where to bridge through to make complex, counterbores and stuff, that it has blind holes. Well, you could kind of measure this one that way, but you can't measure these. I mean, there's no real good way of, you can measure it this way and then you can kind of like guess, but I don't like guessing. Guessing's poor engineering. So we measure that blind hole, we get 2.78 millimeters. You can go through and measure it. You want to measure those kind of holes closest to the end, 2.72 millimeters. And you could go through the whole thing, no pun intended, and measure it. There's another blind hole there. If we're lucky, that will actually fit. Yep, what do you know? It fits in there. So you just kind of like got to measure that. And sometimes, if it's like sticky like this, this is where the thumb screw on the top comes in handy, that you can lock that down by twisting it. And that way, it doesn't allow it to move, and you can actually keep that dimension for you. So anyway, this one, you want it not totally loose, but you can lock it down. But there you go, digital calipers. That is one tool that is totally essential for rep wrapping or 3D modeling, and it's not only good for being able to tweak your machine and make better machines, but it's better to be able to design or reverse engineer new parts that you want to do. So let's take a real-world application. One other thing that you could use it for is, say you wanted to know mounting holes for a circuit board. Now, this is a Sanguilolu board, I think that's how you pronounce it. And you see there's 4 big holes that are around there, and you need to know like how far they are. Well, I mean, tape measures are poor ways to actually be able to measure that, and so you can go through, and what you would do for something like this is to be able to measure, we're trying to be a little bit gentle with this, we don't want to shock anything, measure the inside hole of one of these holes, because we want the center location of where you would drill from the center of this to the center of that, and then from the center of this down to the center down here. And so one little trick to do is to use this 0 button. That's very, very handy. So what we do is we put that in the middle, and we see 3.71 millimeters. Let's go back and try this one. And that one says 2.74 millimeters, 2.73. So what we're going to do is when it's about 2.73, 2.74, somewhere in there, we're going to click on 0. So now that says 0, so when we close it, it says 3.73 millimeters. And we open it up, and it says it's 0 roughly. Okay, well, what that does is that subtracts 3.73 millimeters from anything I measure from now on. And so what I'm going to do is I'm going to measure the hole-to-hole distance between this hole and that hole. That will tell me the center-to-center distance. So when we want to drill it, I think that's probably 43 millimeters is what it would come out as by that's probably 94 millimeters. Let's go down here and measure this one and see. Yeah, about 94, a little bit under that, but I can pretty much guarantee you the circuit board maker made it. So let's switch to inches and see. 1.7 inches, because circuit board makers like decimal inches for some reason, by 3.7. So that's 1.7 inch by 3.7 inch, or you can use millimeters if you want to. But that's kind of nice to be able to switch from millimeters to inches, and then if we go back, it subtracted 1.47 inches. And that's probably a 0.15 inch hole, because that's a pretty standard circuit board hole. If you're lucky, you have actually a blank circuit board, and that's even easier to measure. I mean, you can measure, you know, outside for that. If you wanted to make a case for this, it's kind of, you know, slide-in thing, then you can actually measure 0.082 inches. You can measure the outside 1.85. Let's switch that to metric. 47 millimeters. And we can measure the distances. Well, that's pretty good. One of the things that kind of comes up, and I think almost all RepRap stuff are about the same, is that the center to center location of these pins. Okay, so if you look at that, you probably can barely see the pins in the black backdrop. Well, what you want to do, same thing, we treat it just like you would a hole or a diameter. We're going to measure just one of them, okay? And when we measure one, if you look, it's still got our offset from before, so we can zero it out if you want to. It doesn't really matter because we're going to zero it again once we get here. So, okay, 0.025 inches. So we zero it out, and that was the diameter, but it's actually square, but we're going to call it a diameter. So between one of them, we look at that, and it's 0.1 inch. It's pretty standard. Between two, 0.2, between three, 0.3. It says 0.303, but that's 0.3. So the distance between each pin, we now know. We can go through pretty much anywhere on the board and see they should always be the same, 0.10 inches. So there you go. You've got a lot of them there, and that kind of helps you. And the good news about that is that this is a Molex style plug-in. You can kind of, for the Molex style plugs, I like to use the servo connectors for those, the female connectors for those, because they go on these pins just perfectly. And that way, if you get your stepper motor backwards, I can just flip it around, and it's pretty easy. It is one thing that you have to actually know which way your wires, which color goes where, but that's kind of nice. So anyway, there's a real-world application of why you would actually need to use calipers, because to measure between these pins with a regular ruler or something, not a chance. You'll get it wrong every time. Anyway, thank you for watching. Digital calipers, that would be a tool that you would definitely want to put on your list.